So in doing this problem here, I'm going to just give you the eigenvalues. Eigenvalue 1 is 2, and eigenvalue 2 is 3. And the corresponding vectors are, for 2, it's 1, negative 1, and 1, 1. I'll let you figure that A part out. For B part, show that the matrix equation, this one, is equal to that given. Well, if we plug our values in, I just actually multiply it out. And so it's going to be 5 halves, 1 half, 1 half, and 5 halves times xy is 6. So the first one is going to be 5 halves x plus half y by looking specifically at these two and those two. And then I'm going to go these ones and those ones. And it ends up, because I know this is a 2 by 2, and this is a 1 by 2, I know I'm going to end up with a 1 by 2, and so the x will go with half x plus 5 halves y, and then times xy. And now when I look at this, it's these two multiplied by those two, and if I work it all out, I end up with 5 halves x squared plus a half xy, because it's the x times that, plus half xy plus 5 halves y squared is equal to, the value over here is 6. And if I combine, if I simplify this, all right, over 2x squared plus xy plus 5 halves y squared is equal to 6, and that is what I was asked to show. It then goes to C part, show that these eigenvalues are unit eigenvectors that correspond to the different eigenvalues. Well, one of the things that we have to recognize is that if I will take this eigenvalue, this eigenvector, if I multiply by 1 over root 2 times, I end up with 1 root 2 over negative 1 root 2. And similarly, if I multiply this one by 1 over root 2 times 1, 1, I get 1 over root 2, 1 over root 2. To make sure that it is a unit length, if I do the magnitude of 1 root 2 squared plus negative 1 root 2 squared, that is equal to 1. So therefore, it is a unit eigenvector. All right, continuing on then, it says, hence show that this is true. Well, one of the things that I want to recognize when I look at this is I have to see that this here is this, and it's this. This is the eigenvector, eigenvector, eigenvector for the eigenvalue of 2. This is the eigenvector, eigenvector, eigenvector of the eigenvalue of 3. And one of the things that I know is true is I know that the definition of an eigenvalue is n times some vector is equal to the eigenvalue times that specific vector. If this relationship here is true, if it's true, then I know that v1, v1, and lambda 1, this is the eigenvalue for this particular eigenvector. And so if I look at what I have here in this particular scenario, right, I can see that here this times 2 is going to be this times m. That is the definition of the eigenvalue and eigenvector. This times n is this one times 3. So therefore they are equal. If we think about this, continuing on, let R inverse be that, find matrix R. Well, I know I take the values of my R inverse here, I switch these, make these negative, and then I multiply it by the 1 over the determinant, which is this matrix here. And then it says show that this is true. Well, if I look here, this is M times this here is R inverse already, is equal to R inverse times 2003. If I multiply by R on this side and R on that side, that becomes just M is equal to this procedure here. Okay, so as I continue along here, let R times little x little y be big X big Y. Well, R is this matrix times little x little y is simply root 2x minus 1 over root 2y. And on the bottom end, it's going to be x 1 over root 2x plus 1 over root 2y. And that is saying what is equal to big X, big Y. Well, I know then that x, those equals x, and that equals y. So I can then also go, well, let's take xy, this one, and our inverse, which I know from above is 1 over root 2 minus 1 over root 2, 1 over root 2, 1 over root 2. And when I multiply that, I get 1 over root 2x minus 1 over root 2y. And I get 1 over root 2x plus 1 over root 2y. And that, I'm told, is equal to x, y. Well, I can see that y is that, which is the same as this y, and x is this, which is the same as this x. And so I have actually shown, I verified that this statement here is true. I've verified that it's that x, y, if this is true, then this is also true. Hence, find the Cartesian equation satisfied by x and y. Well, here's some interesting connections we have to make. These problems are all about connections. So if I consider going back to the very top, here is the equation that I'm looking for. I have xy, little xy, m times xy, little xy is equal to 6. Well, I know from here that m is equal to r inverse m r. No, sorry, let me rephrase that. Not m. Here m is equal to r inverse with the eigenvectors inside here. So 2, 0, 0, 3 times rxy is equal to 6 xy. Well, I just learned, if I look carefully over here, if I look down here, that rxy is big xy. Well, that's rxy is big xy. So 2003 is big XY, and I also know from over here that big XY is equal to that. So I know that this is big XY is equal to 6. And so now if I multiply these, I get 2x 3y times xy is equal to 6, or 2x squared plus 3y squared is equal to 6. And these are big x's and y's. So I've found the Cartesian equation satisfied by that. So now when we go to this here, we have, if I multiply this, I know that I can say that this multiplies to 1/3 capital X and 1 over root 2 capital Y is equal to UV, which means that these are the same and those are the same. And so I can multiply big X is equal to square root 3 times U, and big Y is equal to square root 2 times V just by doing multiplication. And then I'm going to take both of these and plug them into here. So when I do that, I get 2 times root 3U squared plus 3 times 2V squared equal to 6, which then is 6U squared plus 6V squared is equal to 6, or I can say U squared plus V squared is equal to 1. Equal to 1. This here is an equation of a circle with a radius of 1. Okay, so now it says state geometrical what transformation the R matrix represents. Well, here is my R matrix here. I recognize these numbers, and it's all about making connections. I recognize these numbers as cosine of 45, sine of 45, cosine of 45, sine of 45. And because we're doing transformations, I recognize that this is a rotation matrix. And so G part, I know that this is a rotation matrix. And I'm going to go this direction anti-clockwise. 45 degrees is what that's doing. Now, state the geometrical shape represented by the curve in big X, big Y, and give a reason. Well, here is the curve big X, big Y. And if I think about what's going on here, I have a circle of radius 1. If I think about this, and if I think about this particular matrix here, this is a stretch along the x-axis by this much, and this is a stretch along the y-axis by this factor. So I end up with a circle, which means if I've stretched it one way with x and another way with y, it was stretched something like this. So it was originally, and I also recognize this form of an equation, which if I divide by 6 is x squared over 3 plus y squared over 2 is equal to 1. That is an equation of an ellipse. But I can get that looking at this matrix down here, right, by the fact that it's stretching it x and y differently. So if this is an ellipse, well, going back to part B, the only thing that's happened in part B, the thing that's happened in this particular thing is it went through a rotation of 45 degrees. And so this particular function is also a rotation. It's the same, it's an ellipse that's been rotated by 45 degrees. So hence the three-dimensional shape presented by this, it is a ellipse as well, rotated by 45 degrees. And then finally, write down the equation of two lines of symmetry. Well, if I take an ellipse and then I rotate it 45 degrees, which I don't think I'll be able to do, but if I take it, rotate it 45 degrees, an ellipse, well, there's going to be a line of symmetry here, which is y equal x, and a line of symmetry here, which is y equals negative x. And that is just by pure inspection. I hope that helps answer a bunch of the questions for this one.